Okay, we're ready for section 2.3. It's called the limit theorems. We already know that the word limit can refer to a lot of different things. Today we're going to refer to a limit as finding a value. So let's get going. First thing is to talk about some terminology. We've got undefined versus indeterminate. Now undefined should know. You should know that some value divided by 0 is undefined. Because the definition of division, for example, is that if 6 minus 2 equals 3, then 2 times 3 equals 6. Using that pattern with this, we would have to say that 0 times something has to equal the letter Q. Well, we know that there is nothing that can fill in that space, so this is an undefined expression. Indeterminate means when we have a function that ends up with 0 over 0. And although there is no solution to this because it's division by 0, we call it undefined. And again, using our multiplication proof of division, if I take 0 times p and say that it equals 0, using this same pattern with this expression, you can see that almost anything, well, anything can be substituted for p. Therefore, we call this expression undefined. Or excuse me, we call this expression indeterminate because you can't determine the value for p. So just some terminology so that we can get going and look at some examples. So we're looking at section 2.3. I hope you have your text open. And they start with a function f of x equals 3x squared minus 48 over x minus 4. And you can see that if we try to evaluate this function at f of 4, we end up with 0 over 0, or the indeterminate form. So f of 4 is undefined because the function is indeterminate. Do you see the difference between that terminology? The value for f of 4 is undefined because the function takes on the indeterminate form. Now, one thing that we can do with this function is to simplify it a little bit. And if I pull out a 3, I end up with x squared minus 16 on top. And then I can simplify the top a little further. X minus 4, x plus 4 divided by x minus 4. And you can see that that will cancel. And I end up with this expression. So my original function is the same as this function, as long as x does not equal 4. So what we're saying is that 3x squared minus 48 over x minus 4 is equal to 3 times x plus 4. We would stop with that in Algebra 1 and 2 and Pre-Cal, but we really need to add the caveat that says that this is true if x does not equal 4, because you can see that if x equals 4, the first term does not equal the second. For all other values it does. But let's go back to our evaluating at 4. If we take our second function and evaluate it at 4, we can get a value, and we get 24. This number is actually the limit of the original function. Take a moment and pull out your graphing calculator and put into y sub 1 the expression 3x squared minus 48 over x minus 4 and graph it. You'll see that you will get the exact same graph, and you might have to adjust your window because this is a line with a y-intercept of 12. You're going to get the exact same graph as we get for our second function, our simplified function up here, except that this graph has a hole at x equals 4. me erase a little bit here. So you should be getting a graph that looks like a line and that has a hole. Now when we're talking about limits, remember we're talking about what happens when we get really close to something or when we make something very, very small. So my graph, which passes through 12 and has a slope of 3, when we get to 4, there's a hole in it. However, the limit as x approaches 4 of that original function does equal 4. So graphically, if we look at it, we can see that as we approach 4 from the right and the left, as we come towards 4 from the left or from the right, we are approaching, 24. We are approaching the value of 24, and that is my limit. You can see that if I simplify the function, and I use my 3x plus 12, I can also get that it equals 24, but this function I can get algebraically because the second graph is the same with the hole filled in. So that's my definition of, or my explanation of limits as we're approaching a certain value. There are lots of rules we can use with limits. Oops, here we go. The first is that the limit of a sum of two functions is the sum of the two limits. In other words, if I have two functions added together, whatever they might be, then the limit as x approaches any value c of f of x plus g of x can be computed by taking the limit as x approaches c of f of x separately and adding that to the limit as x approaches c of g of x. In other words, I can break a complex function down and get two smaller functions and find their limits. Let me go ahead and write the rest of the rules and then we will look at some examples. If you'll pause the video to write these down, they are the same idea having to do with products and quotients. Alright, so if you look at page 40, there is an example of two functions where f of x equals one function, 2x plus 1, times the function 5 minus x. And we want to find the limit as x approaches 3. So we want the limit as x approaches 3 of f of x. If I define this little function as, what did they use? Yes, g of x, and this little function as h of x, I can say that this is the limit as x approaches 3 of g of x times the limit as x approaches 3 of h of x. And you can see that on the graph they've actually broken that down as to two little graphs, linear functions, g of x and h of x, and a parabolic function for the product. And when you find the limit as x approaches 3 of g of x, which means I'm plugging 3 into my g of x, and then the limit as x approaches 3 of h of x, you can see that I'm going to get 7 times 2, which is 14. So breaking it down, I can do a simple product of each limit individually. They also give an example for the quotient, the idea here being that we can break down a complex function to get two simpler functions to work with. In this example, I actually wouldn't bother. I would just plug 3 into this whole thing, which you can see is really what we're doing here. But as functions get much more complex, it's important to know that we can break them down and work with them in smaller pieces. If you look at page 42, and please pause the video to look through these function properties of limits. You don't need to copy them into your notes. You just want to make sure that you have an idea of where they are. So let's look at example 1 on page 42. it asks us to use the limit properties to prove that the limit as x approaches 3 of x cubed minus x squared minus 2x minus 12 over x minus 3 equals 19, and we want to prove this. You can see that if we try to plug in x equals 3, we're going to get the indeterminate form. So I can't just substitute. I can, however, use factoring to break this down into smaller pieces. Now, if you don't remember how to factor a 4-term polynomial, let's go off to the side for a minute. There are two ways to do it. One is to try grouping, and if I try grouping, you can see that I don't get matching binomials to work with. So the next way to factor is to use synthetic factoring. So factors of 12 that we are going to put 1, 2, 3, 4, 6, 12 over the factors of the leading coefficient. Those are my choices, and I'm going to use my coefficients. Excuse me, back up here. I'm going to use my coefficients 1, -1, -2, -12, making sure I'm not skipping any powers, and try 1, 2, 3. I'm going to skip right to the fact that 3 will factor for us. So we bring down the 1. 1 times 3 is 3. Adding, I get 2. Bring up the 6, 4, 12, and 0. So if you remember, that means my factors, I'm going to rewrite my numerator, are x minus 3, this is the opposite, and then these become x squared plus 2x plus 4. And you can see that at this point I have two choices. The example continues on by finding the limits of each of these individual pieces. No, excuse me, I'm sorry, they don't. They go ahead and cancel. So we're going to cancel, and we're going to say that we are now looking for the limit as x approaches 3 of x squared plus 2x plus 4 when x does not equal 3. Now this seems like a contradiction, because I'm saying I want to find the limit when x approaches 3, but x can't equal 3. But remember, when we're talking about limits, we don't need to equal the value, we just need to get really, really close. Now's where they break it down to use our properties. So they're going to take the limit as x approaches 3 of x squared plus the limit as x approaches 3 of 2x plus the limit as x approaches 3 of 4. This becomes 9. This becomes 6. And what about this one? The limit of x as x approaches 3 of 4. Remember, this is a function description. This is y equals 4. Therefore, it's a horizontal line. In your book, this was property, the one at the very bottom, the constant function identity. This is the last property on page 42. So no matter what x value I choose, my limit is always 4. Okay, therefore, the limit of the function is 19, and that's our proof. So this chapter is going to ask you to break down functions a bit, and again, I'll say one more time that this is for the uses of learning how to use these properties. If I got to this point, excuse me, I should include this. If I got to this point in a problem, I would just go ahead and plug 3 into this polynomial. There really, in this case, is no great need to break it down into our 3 pieces. But for the sake of learning the properties and understanding the properties, that's what we're going to be doing in this lesson. Then when we do need it, as things get more complicated, we'll have that tool to use. And that's it for section 2.3. It was a quickie. So we will work on these problems in class, and I hope the videos went well.